Okay, so good afternoon and welcome back to the live sessions on mechanics and control of robotic manipulators. Regarding this week, we would be, this is basically the second last week for the course. And for this week, we'll be discussing contents related to motion control of robotic manipulators. So until this point, we have covered all the topics from all the way from kinematics, kinematic modeling, differential kinematics. We have also covered dynamics. And in the last week, we have also covered trajectory planning of robotic manipulators. And for this week and the week following the current one, we'll be mostly focusing on developing motion controllers. So this is more or less the ultimate, basically the final aspect of a design of robotic manipulators. So yes, I hope you have gone through the lectures of week 7. So with this live session, the intention is to summarize the key points that has been discussed in the lectures covered by Dr. Shant Kumar Mohan. And we'll also solve some sample tutorial questions that could be beneficial for those of you who are solving the quizzes as well. Okay, so yeah, we'll get on with the session. But in case if you are not following something that I'm saying, or if there are any technical issues, please do let me know. Okay, so for the syllabus of week 7, we have been basically introduced to robot motion control. So the first few lectures are dedicated to give you or to impart you some brief introduction to robot motion control. And we have also covered various kinds of manipulator controls and their features actually. And we have basically the courses also deals with the design of two different kinds of control, mainly what we call kinematic control. And in kinematic control, we have also seen two classifications: open loop as well as closed loop. And in this week, we have also covered some MATLAB simulation of kinematic control for standard RR robotic manipulator. And finally, we'll conclude the week with discussions on dynamic control. But again, we have come across open loop dynamic control as well as closed loop dynamic controls. Right? Again, like just like the previous week, I would really urge you to go through the MATLAB simulation videos also, because in the lectures we are mostly dealing with the design of robotic control of robot motion controllers. We would be mostly dealing with a single variable. It may look like it's only dealing with a single variable, but when it is put into practice in case of a full-fledged robotic manipulator, there are some intricacies that are basically easy to miss if you only follow the lectures. And hence, I would urge you to go through the MATLAB simulation lectures as well. Okay, so moving on to the actual syllabus, we'll start talking about the introduction to robot manipulator. So basically what it says is that the motion control is basically a subfield of automation, right? Encompassing the systems of the systems or subsystems involved in moving parts of machines in a controlled manner. Right, so motion control purely deals with motion. It's not really concerned with how the motion is achieved. So, for instance, like if we have a set of rigid bodies, as in the case of a robotic manipulator, and we would want the motion, or we would want to move each of these rigid bodies in a controlled manner. And for that purpose, we would basically deals with the design of motion controller, but the forces that is developed as part of controlling a set of rigid bodies is not taken into consideration. So it does not matter how large the forces are basically coming up. The forces part is basically not really taken into account in case of a motion controller. Only the motion trajectories is the controlling of a robotic manipulator or a set of rigid bodies through a particular trajectory is the only matter of concern. So for the point two basically says a motion controller contains the motion profiles and target positions for the application and creates the trajectory for the motors and or the actuator. So just like what we have seen in the previous weeks, the motion controller basically identifies the start and end position where or how we would want to move the robot. And it basically creates a trajectory or a profile, a motion profile in other words. So if you want to make a robot or make an end effector move from initial position to a target position, there could be multiple ways you could achieve that. You could plan a trajectory based on a cubic polynomial. You could plan a trajectory based on cycloidal motion. All sort of possibilities are available. And motion controller basically takes care of all those things. It will basically create a trajectory based on the requirement. And like these are the basic definition of motion controllers. And why do we need motion controllers? That comes in the second part. It says like robots similar to many engineering applications. For robots similar to many engineering applications, it's impossible or very difficult to obtain the exact dynamic model of a robot due to many unavoidable reasons. Right? So like we have seen how to derive an equation of motion of a robot manipulator. It's something of this form. A mass matrix Q times an acceleration vector Q double dot plus N of Q dot plus G of Q, maybe the gravitational vector, would give you the torque. But again, like there is a limitation in how we would basically estimate this mass matrix. There would be some uncertainties in deriving this mass matrix, these vectors, all these vectors. Because like if you obtain this data from a CAD model, like if you design a robot from a CAD model, that is sufficient. You could easily extract the parameters, the mass, the inertial as well as the mass parameters from the CAD model. But once you fabricate something in real life, like there could be it won't be exactly matching with the CAD model. There could be some additional things that that could be not included in the mass matrix. And there are other terms. There are even unmodeled terms that does not comes that is not covered by these terms. There could be friction. Unmodeled terms. MOD. Unmodeled terms. Those could be friction. Dampings due to viscous damping as well as friction, Coulomb damping. All those things we are not covering in this model. It could be accommodated, but still it wouldn't be an exact model of what we can expect in the real life. Right? So even though we do the dynamic model, it's very impossible or it's very difficult to obtain an exact dynamic model of a robot due to many unavoidable reasons. Right? And the second point says, like, moreover, the presence of external disturbances and parameter variations are inevitable in robots. Right? Due to friction and wear and all those things, the constant parameter that we consider as constants could be a function of time due to the influence of wear and other external disturbances. And like we also have some external disturbances, maybe due to change of external forces, vibrations in the basis. So lot of external factors that is not modeled by a dynamic model could also come into play when the robot is operating in an actual environment, right? And with that, like good performance cannot be reached without advanced controllers. So because of these facts, because of these factors, like due to the external disturbances and parameter variations, and due to the fact that we don't have an exact dynamic model, we would require a good motion controller in order for us to offset these factors, right? In order for us to counter these factors. Okay, so in the lectures we have also covered the evolution or how the design of robot motion control have evolved. So it basically started from the mid-70s where we had exact models, but we had no sensing. right? So the dynamics of the robot, how much input or how much torque or how much velocities we should be giving onto the motors was purely governed by the equations of motion. This tau would be given by something like this: m of q, q double dot plus n of q, q dot plus g of q, plus there could be some other terms depending on how you model, right? So the input that you would be giving onto the actuators was solely relied on the models. There are no sensing or there are no feedbacks from the sensors, right? That was from the mid 70s, and a decade later, we have something called a reactive paradigm, where we would not rely on the models, but we would rely on the sensors basically. So if we have a target position, maybe a target joint position denoted by Q target or Q desired rather, and currently where the robot is, that is something called Q actual. And based on the difference between the desired and this actual position, we can give an appropriate control input. It could be based on the derivative of this difference. It could be based on the integral between this difference. It could also be based on, it could be a proportional control input based on the, just purely based on the differences between Q desired and Q actual. So it was purely based on feedback, purely based on sensor feedback, and we were not using models during mid 80s. And during 90s, people started combining the model based as well as models as well as sensors actually. The dynamic models of robots as well as sensors or reactive at lower levels. So higher level means at the manipulator level, like the motion of the manipulators, and the lower level basically means the sensors. So the actuators rather. So actuators would have their own dynamics, right? Their own dynamics because of their own inertia and their own, its own inertia and so its own rotational masses and all those things. So at lower levels, at actuator levels, we would use a reactive paradigm, and at higher levels, at manipulator level, we would use classical approach using models. And later during mid 90s, with the advent of probabilistic robots, we were able to integrate sensor data, seamless integration of models as well as sensing. But we also were able to acknowledge that the models were always going to be inaccurate because of the reasons that we have seen in the previous slides. And sensors may also have their own errors, due to background noise and all sort of other issues. That's an entirely different issue actually. So with the advent of probabilistic robots, we were able to sense, or we were able to predict what would be the current shift based on the readings, based on where we are, and based on the sensor readings, what should be the next update. So that was happening during the advent of probabilistic robots. And since 2015, we have data-driven, deep and reinforcement learning-based robot motion control, where the motion controller is mostly driven by data, basically, using machine learning and deep learning and all those things. So initially, you will have to have a large set of data in order for you to train the robot model based on different scenarios, and based on its training, it can basically update itself on what to do further or what step it should proceed further. So that was all about the evolution of motion control, starting from classical robots purely based on model, all the way to the recent approach using data-driven, using the data set. Okay, so regarding the main steps in robot motion control, these are basically the 3 steps in order for us to design a motion control. We have to familiarize with the physical problem under consideration. So with what we have in our hand, we have a robotic system. We need to know how to model its dynamics. So like in the previous lectures on the previous weeks, we were able to do so based on two different approaches using Newton-Euler method or Euler-Lagrange method. How to model the dynamics of a robot. That covers the first 2 points, familiarization with the physical system as well as modeling. Then the third part is basically the control specification. Like how quickly we want our controller to respond, or how or what is the specification of the state space, the steady state error, in what time should the steady state error should be realized, all these sort of things. Like for example, a simple example could be like if this is our desired output, if a step input is our desired input of 1 unit, our controller would take some amount of time to reach from the 0 state all the way to the steady state of 1 units. And the controller specification would tell you how fast you can achieve this steady state. Maybe it can reach slowly or it can reach fast. There could be other priorities. If there are some sort of damping oscillations, you could the controller specification would also tell you, how quickly the oscillations should die out. How quickly it should die out. Should there be an oscillations at all? And like within what range of the final state it should settle. Like the steady state should settle within a few units of the final control input. Those all comes under control specification. Yeah, and we also have some control objectives. In order for us to define the control objectives, these are basically the primary control objectives. The most important objective would be to ensure the stability of the system. Like we would want our robot to converge to the desired position. We do not want it to the control input to increase exponentially. And regulation in the sense, like we would it's an alternative name is what we call as set point tracking, right? So if our robot is at an initial position x0 and we would want the robot to move at a goal position, we would want it to move it to the goal position without much drama. That is what we call regulation, not as a function of time. The third aspect is trajectory tracking. We would want the robot to track a series of points as a function of time. So that is basically what we call trajectory tracking. And the final objective is optimization, mostly related to tuning of the robots, of the motion controller. How we tune the gains, how we tunes the the proportional derivative and integral gains of the PID controller. All those sort of things comes under optimization. Okay, then we also can classify the motion controller based on the following methods. The first method is what we call a motion-based method. So just like what we have seen earlier, similar to the reactive paradigm, we do not rely on the model. So again, what I mean by the model is the dynamic model of the robot. If you write that in the task space, it will be something like the mass matrix times q double dot and acceleration vector plus n of q dot, the vector of Coriolis and centrifugal, plus whatever other terms that you can model. But in case of a motion-based controller, we don't take the model of the system into account. We purely rely on feedback or the feedback base coming from the sensors, right? And the advantage of is that these are very easy to use. Like if we have a sensor, you can easily take the feedback of the sensor. You can basically compare what the measurements from the sensor with what your desired values are, right? And based on that, based on the differences between the actual and the desired quantities, you can give the control inputs. You can give the corrective actions. But these could be the drawback is that these could be sluggish. They won't be as fast as you would like, and it could also produce some poor tracking for performances. Because like the sensor-based data is not always ideal. They have their own noises, they have their own issues. And if you purely rely on sensors, like if the robot is heavily disturbed, if there are a lot of external disturbances, and and all the other uncertainties, the tracking performance could be very poor if we rely on a purely motion-based control method. And then we have something called a model-based control. So instead of using sensors, we have the other extreme. We can purely use the model. So it says that these are comparatively efficient and simple. Right? We basically know how to derive the model of a robotic manipulator. Right? And if we can exactly mimic, or if we can exactly model the system characteristic, these are comparatively efficient because we already know how the robot is going to behave as per this expression. Right? But the catch is that we'll have to accurately model all sort of things that is going on in robotic manipulation. Right? As you can see, in this case, there is no friction term. Right? If there is no friction term, then the actual manipulator should also move without any friction. But if this is how we model, and in the actual robot there are some issues due to friction, then it may also not even work. Right? So that is the catch. So whatever whatever we are observing in the actual system, we should be able to thoroughly model using some approaches. So those are the broad classification of robot motion control based on whether it is model free, or it is whether it is purely on motion based or whether it is model based. Yes, and then where there are a few other classification of robot motion control, right, based on the constant physical parameters, whether the constant physical parameters are accurately known or not. So, like, what are the constant parameters in a robotic manipulator? We know the constant parameters such as link lengths, the location of the center of gravity, the moment of inertia of a link, the mass of each of these links. These are the constant parameters of a robotic manipulator. So, depending on whether or not we are able to accurately get, or we are able to accurately estimate these constant parameters. So those are the basis of the following two control strategies called robust control as well as adaptive control. So robust control is essentially controlling of a robotic manipulator with a small error, a class of robotic manipulators. In this case, the model is not accurately known with the same controller. Right? Like for an example, like we design a robot manipulator, right? And it may have some external disturbances. Maybe, for example, if you consider a robotic manipulator having some sort of an external disturbances of 2 newtons, at one of the end effector coordinates. But we'll never be able to estimate the exact force because it's uncertain. It's not within our control. It's due to something that is out of our hand. And like while designing the controller, we can basically design in such a way that a large amount of force is always going to be acting on the robotic manipulator, maybe the likes of 100 newtons or something. So we can model something based on a threshold, a higher threshold, right? And the reasoning behind this assumption is that no matter what happens, this external disturbance are never going to exceed what we are actually modeling it for. Suppose like if you are modeling it for 100 Newton, and we are also sure that the unknown external disturbances are not going to exceed this thing, then we can basically control or basically control the motion of the robotic manipulator. And that is also called an overwhelming control because like for a 2 Newton, approximately 2 Newton, we are basically considering it to be a 100 Newton force. So the control input would be accordingly very high. So that is, in one way, it is also called an overwhelming controller. And the second thing is it also deals with the uncertainty in system parameters. There is no higher limit of 100 Newton that we have seen in the case of a robot controller. This is it basically deals with uncertainty in system parameters, or rather unknown constant parameters, but it requires the precise knowledge of the structure of the system. So like even if we don't know what the exact system parameters, we should be aware of how in what order these parameters would come into play into the dynamics of robot. But we all know that the friction is basically the square of velocity. So the structure is already known, but even though we don't know the exact value of the damping coefficients. So that is all about this adaptive control and the difference between robust and adaptive control. And yeah, moving on, we also further have a classification that we would explore in detail in upcoming slides. So the first one is called kinematic control, where we would only consider the kinematics of the model. We are not really taking the inertia or the dynamics of the robots. The inertia, the forces or the torques contributed by inertia and all these other things. This can be only valid if the robot is slow, if it is slowly moving, right? For example, like if you have a robotic manipulator, obviously it is going to be having some sort of a mass, and it will also have some sort of an inertia, right? Because these are all physical link lengths. But if the robot is moving very slowly, very slowly in a quasi-static kind of a way, the inertia and the effects due to the masses and inertia won't necessarily come into picture. It can be neglected. So that is where we would use kinematic control, because it's much simpler. If the we don't really have to derive the dynamical equation of motion of a robot if the lot of terms can be ignored because of how the robot moves. That is about kinematic control, where we would only the kinematic models are used. And the second type is called dynamic control, where we would also consider the robot dynamics, where the robot dynamics and actuators are also taken into account. Even the actuators are also taken into account, because actuators have their own mass and have their own inertia. So just like how we derive the equations of motion of a robot manipulator, we will also have to model how the actuators also behave, something similar to the equations of motion of a robotic manipulator. And there are something called cascaded, a dual loop robotic manipulator, where we would consider the kinematics at an outer loop, and based on the kinematics, we would propagate it into an inner loop where it would where it would take dynamics into account. So this thing we will see later in the next week, lectures on the next week. And so far for this lecture, we would limit ourselves within kinematic control and dynamic control. Okay, then we also have a general classification based on the interest or application. We have something called a motion control that we would be seeing later in the slides, motion control, where our objective is to track a robot or guide a robot through a series of points at a specific time. So we don't really bother about what are the forces, or we don't really bother about the limits, actuator limits. We are only concerned about achieving a trajectory, and we disregard the forces that arises as a result of realizing those trajectories. And there is something called force control. Like for example, like if we want to control a rolling ball or a moving surface, for example, like if we have a robotic manipulator, something like a platform, and we have a ball that is rolling over the platform, and we want the robotic manipulator to balance the platform so that the ball will never fall out. So based on where the robot is, where the ball is actually, you can use force control to actively track the ball so that it won't really fall off. Then we have something called hybrid control, where we would use the combination of both forces and motion control in some situations. And there is something called an impedance control. So that basically deals with how a robot interacts with an environment, It basically deals with how a spring mass damper kind of a system interacts with the robot. Mostly, the application comes mostly in teleoperated robot. Like if we, if an operator controls a control module, we would want a slave robot, a robot that is a slave to, amplify or how do you say that? To transfer the motion onto its own working environment. So based on that, it will be able to transfer the stiffness, the compliance and all those things should be transferable. And that is basically made possible by something called an impedance control. Okay, so what Sahil says, I've got a question, but for real robotic arm, we have to use all sort of control. That is exactly correct. Because if you want a robot arm to grasp something and to move it from one point to another, right? The grasping would require some sort of a force control or impedance control. Because like if the object to be grasped is fragile, right? If we use too much of a force, it will break. So based on this force control or impedance control, we'll be able to apply the right amount of force to grasp an object. And we could use the position control to move this object from one position to the target position, right? So if you are only using this force control, right? If the robot is not interacting with any sort of objects, it'll move very fast. That is not a good. That is basically not a good thing to have, because like in the absence of a force, if a robot is moving very fast, there is a high risk that it can injure something. It can injure something that comes within its workspace. Whereas if we go for an impedance control, it won't be like that. It will basically comply around. If it encounters an object, it will try to comply around this object. So if you are talking about a fully real robotic system, one of these things will not work. You'll have to have a combination of all these sort of things in order for a system to actually work. In case of a fully fledged robotic manipulator. Because if you are implying, if you are only implementing one specific thing, just like a motion controller, it won't take into consideration about how much force it should a gripper should put onto grasping an object. It won't take that into consideration. But we know that's very important. And if we take the force control only, if you only take the force controller, in the absence of a force, there is a chance that the motion could be very fast. And if anything comes into the workspace, the effects could be very bad. It could be very detrimental. So in that regard, we would, in case of a real robotic system, we would need all the four. And the further classification is based on the space that is considered, how the control activity is basically considered. So whether the objective is defined on the joint space, we can have a joint space control, or whether the objective is defined based on task space. So this is more common actually. We could have a task space control, and if the objective is based on the sensor space, we can have a sensor space control. And for the course, we'll basically cover these two aspects: how to control a manipulator in task space, how to control a manipulator in joint space. Both of these aspects we will, look into in more detail for this course. And a few more things to be noted. In case of motion controller, we have two separate instances of motion controller, something called a set point controller, right? And we have something called a tracking controllers, where like if we have an initial position, maybe eta I, and if we have a goal position, eta O, the reference vector is always going to be constant, right? It's not a function of time. We only have a start point and we only have an end point. It's not a function of time. That is something called a set point control. And in case of a tracking control, like how you would arrive from an initial position to the goal position as a function of time, right? If we have a trajectory like this, the robot will definitely have to go through this trajectory If we have a different trajectory like this, the robot will also have to follow that specific trajectory. That is what we call tracking controllers, where the reference input, all the time the reference input is going to vary as a function of time. Okay, so now we will look into few of the controllers. The first being a kinematic control, right? So essentially, we know what the kinematics of a robot, how a kinematics of the robot can be represented, right? We have this equation, eta dot is j of q times q dot, right? I hope you can recall this equation where this is the velocity. Sorry, it's a vector though. It's not a scalar. It's a velocity vector in task space. And this would be the velocity vector in joint space. And the mapping is actually made possible by this Jacobian matrix that is specific to that is dependent on the manipulator under observation. Okay, so what do we do in kinematic control? So we know the elements of this eta vector. That would be the velocities of this end effector. Like if it is a 2D robot, if the robot is of 2 dimensions, this could be x dot and y dot, the Cartesian position, the Cartesian velocity coordinates. And this could be the velocity of the active joints, could be theta 1 dot, theta 2 dot, if you are talking about a 2R robot. Okay, so yeah, so in this case, the inputs to the robot, like I'll explain this with the context of a 2R robot. Okay, so we have basically two links. So this is an actuator. This is also an actuator. We have an end effector over here. And if you want to control a robot to follow a specific trajectory, the inputs are basically given onto these actuators in the form of velocities, because this is a kinematic control, right? So the vector q dot, this will be the input to the actuators. Input to the actuators based on some specific output. So we can define the output, we can decide output either in task space or in joint space. So depending on how you define your desired trajectory of a robot, the input could vary actually. So we'll look at this specific case, right? So if you take a look at point 1, we define the desired inputs or the defined desired nature of what the robot should be tracking to be. We have a desired joint positions. So at an instant of time, at a given instant of time, we want the robot's joints to be as per this vector q desired, and we also want our robot to be executing this trajectory at a desired velocity. So we have two such quantities, desired positions as well as desired velocities. And notice that these desired quantities are mentioned in joint space, the variable q. You could do that, or you could do that in the task space, mu desired or mu dot desired. So here in the task space concerns with the velocities and positions of active joints. And if you define that in task space, it basically deals with the positions and velocities of the end effector. Right? If we are talking about an RR robot, the end effector positions could be x and y, desired x and y, x desired, y desired. And the end effector velocities, mu desired dot could be x desired dot and y desired dot. Right? And what are the terms that we that are available? So the available terms are the Jacobian matrix. We know how to derive or how to define the Jacobian matrix of a given manipulator. We have seen that in the previous week. And our objective is to find the control input that we should be giving onto the robot manipulator. So control input in the sense like how much of control input we should be giving or we should be inputting onto these active joint variables so that the robot can execute a desired trajectory, right? So in order for us to execute this thing, the control scheme is as follows. Like this is a purely open loop or a feed forward control, right? So whatever desired velocities that we have over here, we would simply plug this onto the active joints. No, there is no involvement of feedback. So whatever desired velocities we have, we plug that onto the joint variables. So that is exactly what this control scheme basically means. Yeah, Q is nothing but Q desired. Or if you are interested to plan a trajectory in end effector space or in joint space, you can convert this mu desired dot into Q desired dot using the Jacobian transformation, right? Q desired dot would be J of Q inverse mu desired dot, right? And then you could use this Q desired dot to plug it into the active joint variable. So this is a purely open loop control. There is no feedback coming. So whatever you have as a desired, you plug it into the robot manipulator. But it may not work. This sort of controller may not work because there are some conditions to be taken care of. Okay. So I got a question from Perumal Swami. At the starting and ending, Q D dot is 0 or not? Yeah, so we'll come on to that topic. So for example, if our robot has to execute a trajectory something like this, sorry. If our objective of a robot is to execute a trajectory something like this, so we are only dealing with a single variable for ease of clarification. So let this be Q initial and this be the Q final. So this is how we would want the robot to move, right? When T, this is a T equal to 0 and T is TF. And consider the case when the initial position of the robot is somewhere else. If the Q initial is somewhere else, if this is Q initial, then if we are employing these sort of controller, right, the robot will basically execute, like if there are no other disturbances, the robot can execute something identical to the planned trajectory to the desired trajectory. These two parts are basically identical, but there will always going to be an offset, right? There is always going to be an offset because the initial conditions, like the initial condition of the where the robot is positioned initially should match with the initial position of the desired trajectory, right? So if whatever I have drawn in the red is basically the desired trajectory, and whatever I have drawn in blue is the actual trajectory. So the start points of both the initial position of the initial position of the actual coordinates and the initial position of the desired coordinate should match. Otherwise, there is always going to be an offset between the initial trajectory and the final trajectory. So that is what it says by this equality constraint. Q desired of T equal to 0 should be equal to Q of T equal to 0. So this is the actual trajectory and this is the desired trajectory, right? So the initial conditions of the desired as well as the actual should match, right? And there is one more constraint also. Q desired dot should not be 0. If q desired dot is 0, right, q dot is also going to be 0. If the velocity is 0, if it is steady state, if the velocity is constant, then this control scheme will not work. Because if q desired dot is 0, q dot is also going to be 0, then there won't be any input onto the actuators. So that is what this this inequality constraint and this equality constraint basically means. Because it should be fairly apparent from these equations, right? And the same applies for the task-based variables also. Mu desired dot should not be equal to 0. If this is 0, then this will also be 0. That means there won't be any control input onto the actuators. And the initial positions of the desired trajectory and the initial position of the actual position of the robot should always be equal. Otherwise, there will always going to be an offset between the start and the set point. So I hope I have clarified your question, right? So this is all about open loop control. So whatever quantity we have as a desired velocities or as a desired characteristic, we simply input that onto the actuators. It's purely an open loop or a feed forward. Okay, so moving on, we now come on to a closed loop controller. So this is something called a closed loop controller. So again, like what are the desired quantities? We have a desired set of positions, right? We have a desired trajectory to be followed, given by q desired and q desired dot. So these are the positions and these are the velocities, right? And for a set point control, the velocity is always going to be 0. It's always going to be of constant velocities. And for a tracking problem, q dot of t is not going to be 0. This is for a set point control. Okay, so then what are the availabilities? Same as of that of the previous case, we have the Jacobian matrix, right? We know how to derive the Jacobian matrix. We also have the actual joint positions of the robot. So this can be obtained from robot sensors, right? Something like encoders. You can obtain the current joint positions of the robot. And just like in the previous case, our objective is to find the control input to the vector. And this being a closed loop, we have several objectives actually. So the just like what we have, I hope you can recall what we have discussed in the previous slide. The most important aspect in designing a motion controller is its stability, right? So as time tends to infinity, the actual position should converge to the desired position, right? Like if we have a desired position, like something like this, and if we start from an actual position, like if this is, for example, if this is desired, and if this is actual, initially there will be some sort of an offset between actual and desired. But as time progresses, the actual trajectory should converge to the desired path, right? As time tends to infinity, it should be asymptotically stable. That is our most important objective while designing a controller. This can be written in a different way. As time tends to infinity, q tilde tends to 0, where this q tilde is nothing but the difference between q desired and q. And this is the desired position and this is the actual position. So as q tend to q tilde, when t tends to infinity, you can write it in another way. Q tilde tend to 0 as t tend to infinity, right? So what would be an appropriate function for that? Like if you define q tilde to be something of e raised to minus lambda t, right? Maybe lambda, yeah, here lambda is not 0, lambda should be greater than 0, right? If q tilde is something similar to this function, e raised to lambda t, what will happen to q tilde as t tend to infinity? So as t tend to infinity, q tilde tend to 0, right? Because t, when it gets very large, this term e raised to minus lambda t gets very large, and e power minus infinity becomes 0, right? And in order for us to achieve the q tilde to behave something like this, our control law is something like this. Q dot should be q desired dot plus a lambda times q tilde dot. Right? How do we achieve this equation? That is how I'll explain now. It's already explained in the lectures, right? So yes, we want our q tilde variable, q tilde, to be mimicking this thing, e raised to minus lambda t. It should be as per this equation, as per this expression. So if I take a derivative of this expression, what will I get? Q tilde dot will be minus lambda e raised to minus lambda. Right? So this will be nothing but q tilde dot is minus lambda q tilde. Right? So this is nothing but an ODE, a linear ordinary differential equation. Q tilde dot plus lambda times q tilde. This is 0. Right? This is a simple ordinary differential equation. And what is the solution of q tilde? Q tilde for this equation is this one. The solution of this ODE is this. Right? So we want q tilde, we want the error to be behaving as per this first order dynamics. Okay, so if we substitute q tilde dot as q desired dot minus q dot, right? If you make the substitution where q tilde dot is q desired dot minus q dot, right? Then what will be q dot? Where this is the desired velocities and this is the input that we would be giving onto the motor, right? This is our control input. Q dot is our control input. So rewriting this, q dot would be q desired dot minus q tilde, yeah. Sorry. So if we substitute this expression onto this expression, what will we get? We'll get q desired dot minus q dot plus lambda times q tilde. This will be equal to 0. So our control input from this equation, q dot, would be q desired dot plus lambda times q tilde. So this is how our control input is going to be. Where yeah, where this is our control input, and this is something called a feed forward term, right? We would be feeding this term from a trajectory planner onto the controller. It comes straight from the trajectory planner to the controller. This is coming from the trajectory planner, and this box is the controller. And this q desired dot is coming from the trajectory planner. So that's why we call this as a feed forward term. And this term over here is something called a feedback term. Because q tilde, this term is nothing but q desired minus q. That is the difference between the actual position and, sorry, the difference between the desired position and the actual position. And where would you get this actual position? You can get it from the sensors. So that is why we call this as a feedback term, and this as a feed forward term. Right? So in order for the error or the term q tilde to behave something like this, e raised to minus lambda t, our control law should be like this. Right? So if this is our control law, it is guaranteed that as time tend to infinity, q tilde and q tilde dot will go to, will go to 0 actually. It will asymptotically vanish. So that is what this is about. A robot kinematic motion control in joint space. This is purely in joint space. You can also derive a similar expression in task space actually, because in case just in case if the desired positions and desired velocities are given in terms of task space, mu desired t and mu desired dot of t. You would want the variable mu to be to behave something like e raised to minus lambda. This is how you would want it to behave actually. Mu tilde should converge. So similarly, just like what we have seen, you can derive something similar to this, right? That will be the task space control. Like if you are interested, I can also show you that. So if the desired positions and velocities are given in terms of task space, our objective is that mu tilde and mu tilde dot should converge to 0 as time t tend to infinity. Right, so our differential equation would look something just like we have seen in the case of task space variable. It will look something like mu tilde dot plus lambda times mu tilde. This will be 0. This should be 0. This is as per the differential equation. So if you obey this differential equation, if mu tilde can be forced to obey this differential equation, this condition can be guaranteed. So again, mu tilde dot is mu desired dot minus mu dot. And if I'm substituting this into the previous equation, we'll get mu desired dot minus mu dot plus lambda times mu tilde. This will be 0. And if this is the case, mu desired dot plus lambda times mu tilde, this will be mu dot. Right? So, but this won't be the control input, because control input is always going to be q dot. Right? Because control input is something that we are giving on to the actuators. We want to control something in task space, right? Or the variable to be controlled is in task space, but the input is always going to be in joint space. So how do you convert this into joint space? We know that mu dot is j of q times q dot, right? So q dot would be j of q inverse mu dot. So in this case, our control input would be a j of q inverse. Q dot would be j of q. So this will be our control input. Right? So this is how the control law would look like in joint space. This is how the control law would look like for task space control. Right? I hope this is clear enough. Control input would always be in terms of q dot, because we are always giving the input to the actuators. This is control law in joint space, and this is the control law in task space. Okay, so now we move on to dynamic control. And just like what we have seen in the previous case, we have two such cases, an open loop control and a closed loop control. So in this case, we cannot neglect the effects contributed by inertia and the centrifugal velocity, centrifugal accelerations, and all those things. So for that regard, we'll take the dynamics into consideration. Right? So we have some desired quantities. We have the desired positions given in terms of joint space variables. We have the desired velocities. We also have the desired accelerations. And what are the available entities? We have this inertia matrix. We know how to derive this inertia matrix. We also have a vector of the centrifugal and Coriolis effects. Right? And the control input as per a simple inverse dynamics is something like this. We basically know the control input tau would be m of q desired double dot plus n of q desired dot. So in case of a dynamic control, this will be the input. The tau vector would be the input to the motors. Input to the actuators. And again, as you might have noticed, there are no feedback terms. These are all purely based on the model, right? So just like in the case that I've explained in the previous section, for a 2-hour robot with 2 actuators, we estimate that control input tau using this expression, using these equations of motion, where we, instead of the generic term q, we plug the desired position, desired accelerations, and desired velocities into this equation. And whatever we get, we simply plug this onto the actuators. And again, just like what we have observed in the case of the open loop velocity control, this will work only if q desired double dot is 0. The desired acceleration is not 0. What happens if it is 0? If it is 0, this term will vanish, right? This entire term will vanish. So this condition that q desired double dot not equal to 0 will always have to be ensured. And for further, we'll also have to ensure that the initial position of the desired trajectory should be equal to the initial position of the actual trajectory. And same in the case of the velocities. The initial velocity of the desired trajectory should be equal to that of the initial velocity of the actual trajectory. Like, for example, like if the desired trajectory starts from a point xy equal to 5,6, if this is the desired trajectory, our actual trajectory should also start at this exact same start position, right? If it is starting from somewhere else, just like what we have seen in the case of the open loop velocity control, there will always going to be an offset between desired and actual. In order for us to avoid this offset, we have to make sure that the initial conditions of velocity and position for both the desired and actual should always be the same. Right. So this is all about inverse dynamics control. This is again an inverse something. This is also an open loop control. Right. And this was purely based on the joint space control. So if the control is supposed to be task space, we know the task space equations of motion. It is something like F would be m of mu times mu double dot plus n mu of mu dot. And in the previous lectures, we have also seen how to write mu dot in terms of mu joint space and n of mu in terms of joint space. And we also know that F, something we also know the mapping between tau and F, that is J transpose F. Because even if the variables are in task space, our input is always going to be in joint space because we are giving the input onto the joint space. So we have to use these expressions for us to finally get an expression on tau so that the robot can be controlled in task space as well. This expression is purely on joint space. So when it comes to task space, we'll have a few more terms. Right. The first substitution is tau is J transpose F. So you will have a J transpose term over here. Sorry, F is, yeah. So if tau is J transpose F, then what is F? F would be J inverse transpose tau. So here it will be J inverse transpose tau. And you'll also have to convert all these terms, mu, m of mu, and n of mu, in terms of its joint space equivalent terms. Then if you take this term onto the other side, you will get an expression for tau. Things like that, yes. Okay, so now we move on to a robot dynamic control in joint space. This is a closed loop control. A closed loop control actually. So again, in this case, what are the things, desired parameters that we have? In case of closed loop also, we have the same desired parameters, the desired positions, the desired velocities. In case of a set point control, velocities are going to be 0. It's not a function of time. And we also have the desired accelerations. And again, just like what we have seen in the previous case, for set point control, q desired dot is also going to be 0. And what are the available entities? So in terms of a feedback control, we have the positions of actual positions of all the joints, as well as actual velocities of all the joints from the encoder data or from any other sensors. We can also derive the inertial metrics and the vector of correlation centrifugal effects. So we basically know the step-by-step procedure to how to derive this mass matrix and this n vector. Just like in the previous case, our control objective is to determine the torque vector tau that is to be inputted onto the or into the actuators. And we also have some objectives. So this being a closed loop controller, our the most important objective. Okay, so we have got a question. I need to answer that in the beginning. So we can't use kinematic control for trajectory tracking. Is this due to the offset between desired and actual? Yeah, but theoretically, like if you can, if you begin from, if the actual position of the robot begins from the actual position of the desired trajectory, then theoretically you can still use. It shouldn't be a problem, right? Because like if this is how you define a trajectory, if this is the desired trajectory, and this is the position, q desired at t equal to 0, right? But if you somehow force the manipulator's initial position, actual initial position, to begin from the same position, then you can still use an open loop controller to track it like this, right? That is not an issue. But the bigger issue is that you will have to accurately model the robot. All the dynamics or all the things should be exactly should be captured by the model. So this will only work provided you have captured all the dynamics using the kinematic model. Otherwise, this won't work. Even if you make it coincident, even if you make the actual and desired position to begin from the same position, if your model is entirely wrong, that won't even work. But based on the assumption that you have captured the model of the robot exactly, the open loop controller can still work if you somehow force the initial conditions of the actual trajectory to be coincident with the initial conditions of the desired trajectory. If that is the case, then it will definitely work. Okay, I hope that is clear. If not, please let me know. Okay, so moving on. So we have covered the desired quantities and we have also covered the available entities. Our objective is to find the control input to be given onto the robotic manipulator. And our objectives, like for any controller, the most important objectives are we have to maintain that the stability of the controller is always going to be stable. Like as time tends to infinity, the terms q tilde and q tilde dot should vanish or it should converge to 0. Just like in the previous case, we defined q tilde to be the difference between the desired and actual positions, and q tilde dot to be the difference between the desired and actual velocities. So how do we basically design a controller so that these conditions can be maintained? This can be ensured. So that is what we look at in the next slide. So like for asymptotic controlling of asymptotic stability of Q tilde dot, the robot should follow this differential equation. This is the second order differential equation. Just like what we did, like if you can recall, for the kinematic control, we force the robot to move as per a first order differential equation, right? Because the solution would be Q tilde would be C1 e raised to minus lambda. And we know that as time tends to infinity, this will converge to zero. But in the case of dynamics, we have to ensure that the robot follows a second order trajectory. We know how the solution of this differential equation would look like, right? It will look like something like C1 e raised to minus lambda t. Sorry, C1 e raised to minus lambda 1 t plus C2 e raised to minus lambda 2 t, right? So as time tends to infinity, this solution Q tilde dot and Q tilde dot will tend to zero as time tends to infinity. So if we force the robot to follow this differential equation, this condition can be satisfied. This condition can be satisfied. And the coefficients are also very important. This lambda 1 and lambda 2 should be greater than 0. Otherwise, as time tends to infinity, there could be a chance that it could increase. It could increase exponentially, or it could be in a metastable state, like it won't without any damping. So if you ensure this thing, the coefficients are maintained greater than 0, and if you force the error to be following this dynamics, this second order differential equation, you can guarantee that the terms Q tilde and Q tilde dot will converge asymptotically to 0. Okay, so simply by substituting this Q tilde dot into these two terms, right? Q tilde is nothing but difference between Q desired and Q desired dot. And taking the derivative, you will get this term will split into these two terms. And the remaining terms are kept as such. And we also know from the dynamics equations of motion, we also know the input to be of this form. A mass matrix M of Q times Q double dot plus N of Q tilde is tau. The further manipulation, how will you find this tau? So this will be tau minus N of Q dot, the whole multiplied by this M inverse. That is what Q double dot equation is look like. Right? So if you back substitute this equation onto this equation, you will get something like this. Right? So your control input would be tau would be M of Q, the whole multiplied by Q desired. There's a desired acceleration plus lambda 1 Q tilde dot plus lambda 2 Q tilde, then plus this vector of Coriolis and centrifugal effects. And just like what we have observed in the case of the velocity control, this term alone is a feed forward term, right? And these two are feedback terms, because these both of these terms consist of a Q tilde term. Q tilde is the difference between the desired and the actual, and both of these two terms are the feedback terms. Right? So if you input this control law onto the actuators, or if you impart this input onto the actuators, you can guarantee that as time tend to infinity, Q tilde and Q tilde dot will, asymptotically go to 0. And again, just like this, you can also derive the control law in terms of task space also. That is also covered in the lectures, right? It's more or less the same procedure. You again want the control law to be following this thing, mu tilde double dot plus lambda 1 mu tilde dot plus lambda 2 mu tilde equal to 0. Right, and using some further manipulations, you have to, there are a lot of manipulations that you have to use, because this mostly deals with the transformation of matrices, or transformation of parameters like pass and this vector n from task space to joint space. You know what this mu double dot would look like, right? Sorry, yeah. The equations of motion, like instead of this equation of motion, in task space, you will get something like F is m of mu double dot plus n of mu dot. This is going to be F. All these sort of things. Okay, so yeah, I got a question from Murali. He says, what is the significance of F in task space? I'm not really sure what you meant by the question. So in task space, this vector F would be the force that is imparted onto the end effector coordinates, Fx, Fy, Fz. But if you use your intuition, it's more easy to see this F, this tau actually, because we know that we are basically giving this as an input to the actuators. Whereas this thing would be simply the forces or torques that is happening on the task space. And the reason is that, like, we mostly plan the trajectory on task space, right? We mostly, like, rather than planning a trajectory on joint space, it's more intuitive to, yes, exactly. Tau is easier to visualize. So we mostly plan the trajectory on task space. And if you write this equation, if you want the robot to behave as per this second order dynamics, you also have this equation of motion in task space as F would be m of mu double dot plus n of mu dot. Right? So instead of this equation, you will have to use this equation. Right? And finally, you will get an expression in terms of F would be something like so and so. And again, finally, you will have to convert it in terms of tau. Right? From this expression, tau would be J transpose F. So F would be J inverse transpose tau. Because no matter what you do, your input will always going to be in tau. But the term inside, see, all the terms inside would be, instead of Q double dot, you will have in terms of Q, you will have everything in terms of mu. But not exactly, because there will be some other terms, some other due to this what do you call, due to this coordinate transformation, you will have some J transpose, you have some J dot variable, all these sort of things will come. So instead of tau being a function of Q, instead of tau being a function of Q desired double dot, Q desired dot, and Q desired, for a task space control, this tau would be a function of mu desired double dot, mu desired dot, and mu. So a task space control is not as simple as simply substituting these values in simply substituting this Q in terms of mu. There are a lot more other terms also that comes into picture, right? Because and the final expression would be a function of mu rather than rather than Q. Yeah, so it'll be a bit more involved. The transformation, like the procedure is again very straightforward, but it'll have a lot more manipulations in order for you to get into this final expression. And you'll have to be very careful about, because that kind of questions, you could get those kinds of questions for your assignments. Right. So whatever I'm covering in this lecture is only for joint space. You may be asked to find out the control input tau in terms of task space also. Okay, so with that, we'll go on to some sample questions. Okay, so these are true or false questions. It says, robots similar to many engineering applications, it's easier to obtain exact dynamic model of the robot. Is it true or false? It's always going to be false, right? Yes, because if it was easier to obtain this exact dynamics of the robot, then there would have been no need to design a controller. And you can proceed with the exact model of the robot to control the robot. Because there are uncertainties, you would have to design a controller so that it can navigate around these sort of uncertainties. So that's a fairly straightforward question. The answer is indeed false. And second question is about adaptive controller. It says, an adaptive controller aims at controlling with a small error a class of robotic manipulators where the model is not accurately known with the same controller by ignoring the effects of unknown effects. Again, like this is a straightforward sentence just taken from the lectures. And if you have listened to it, this entire sentence is applicable to robust control. This is not a sentence for adaptive control. Yes, so in that regard, this is also for false. This is mostly true for robust control. Because like we don't know what the uncertainties, we'll anticipate it to be something very high. And we use that thing to compensate for all the errors that is happening within that higher bound. So it's in another way, it's also called an overwhelming control. We anticipate the disturbances to be very high, and we will incorporate some very high penalty or very high control input to compensate for all the unknown disturbances that will basically happen within that uh, yes, within that action, control action. Okay, so moving on to the third question, it says, if Q desired and Q desired dot are the desired joint positions and velocities, then the computed velocity control can be given us. So the computed velocity control is what we have seen earlier in the case of the closed loop kinematic control. That another name is computed velocity control. And in the case of the closed loop dynamic control, we also call it computed torque control. Right? So what is the correct expression for I've got the answer to be option 4. 1, 2, 3, 4. This has to be the option. Is that correct? Because we saw we want the robot's dynamics to be following this. The first order dynamics q tilde dot plus lambda times q tilde to be 0. Right? If we follow this differential equation, our solution q tilde would be something like some constant times e raised to minus lambda. Right? So if you substitute this q tilde as q desired minus q, then this term would be, sorry, lambda times q tilde, this will be 0. And now our control input q dot will be q desired dot plus lambda times q tilde. So this is our computed velocity control. Right? This is also a feedback control, out of which this is the feed forward term, and this is the feedback term. So I suppose the correct answer is option, it's 3, right? I'm getting it as option 5. Yes, it's option 5. Yes, correct. Because, yes, the correct answer is indeed option 5, because from here we know Q tilde is Q decide minus Q dot. Yes. So option 5 is indeed the correct answer. Okay, so moving on to the fourth question, it says, the inverse differential kinematics or inverse dynamics is equal to, is it a feedback or a closed loop control? Is it a feed forward control? Is it a motion based control? Is it a robust control? Is it an adaptive control, optimal control? Which are the correct options? So inverse differential kinematics or inverse dynamics control. So inverse differential kinematics is something like Q dot is Q desired dot, or Q dot is J of Q desired mu desired dot. This is inverse differential kinematics. Yeah, and for inverse dynamics, we know tau would be m of Q decide double dot plus n of Q decide dot. So if you supply the trajectory in terms of mu and mu desired dot and mu desired, you can estimate the control input in terms of kinematic control. Or if you give the trajectory in terms of Q desired dot and Q desired double dot, you can compute the input, the force inputs in terms of this equations of motion. So in that case, both of them have one thing in common. Both of them are basically a feed forward or an open loop control. Actually, yes, that is indeed correct. Okay, so moving on to question 5. Finding the joint torques for a given set of joint angles, velocities, and accelerations as input is known as forward kinematics. Anyone know the answer? Because it deals with the torque, so we can straight away eliminate kinematics, all the kinematics, right? So it should be something of option 2, option 3, option 4, I suppose. Option 6. So you know the equations of motion to be tau would be m of Q decide double dot plus n of Q dot. So if you give the trajectory Q desired double dot, and Q, finding out the joint torques is, yeah, that is inverse dynamics actually, not forward. Forward would be the other way around. That is indeed the correct answer. And the final question, read it carefully. So we haven't covered a proportional integral controller for during this discussion, live discussion, but it has been covered in the lectures. So in this regard, it says the expression for proportional integral controller with feed forward term is. If you can recall it from the lecture, which would be the correct option? So yeah, this is also a kinematic control because we are also not taking dynamics into account, as you can see from all these equations. So the control input Q dot would be some feed forward term Q desired dot plus the proportional controller would be some gain times the error that is proportional to the error basically, plus integral will be the some constant gain multiplied by the integral of the error. That will be Q decide minus Q d. So this is the feed forward term. This is the proportional term. And this is the integral term. So out of which is the correct answer? I'm getting the answer to be option 6. Is that for the previous question or this current question? Q decide dot plus. I guess it is option A, right? Option A. Yes, option A. Yes, correct. That is indeed the correct answer. Yeah, so yeah, we'll wind up early this session. That's about it. And for the tutorial questions, you can expect like whatever we have discussed, you can expect questions similar to this. And on top of this, like we have only covered the design of motion controller in joint space. But in the assignments, you could also get, if our objective is to control the robot in task space, then what should be the control law? How will the control law be? So you should be confident to derive the control law for the objective defined in task space also, right? So again, the procedure is also straightforward. Whatever we have discussed in the session, or that is valid, but you will further require some coordinate transformations on top of what we have discussed in the session. You will also require some coordinate transformation. We have seen that in the previous weeks. How to map between the mass matrices, how to map between the Coriolis vector, for task space and joint space. All these sort of things. So you could also expect those sort of questions for your assignments. Yeah, so with that, we can wind up the session. Next week we'll discuss on week 8. It's we'll also discuss something called a cascaded control. That's for week 8. And at the end, we'll also discuss how to uh, model a mobile robot, like with whatever we have covered until now, starting from kinematics, then dynamics, then trajectory planning, all the way to motion controller. We'll also do how to do that for a mobile robot instead of manipulator. Okay, so if you have any questions, I can take it, or otherwise you can consider this to be the end of this session. Okay. Okay. Thank you. Yes, that's it. Thank you. Okay, so if there are no more questions, I'm logging off. Thank you.